Hello, hello, hello. We should be live. Need to double check that. Okay, looks like we are indeed live. Yeah. All right. Late night stream. Um, just really following up on Monday stream, where we basically got introduced, just started to learn about machine programming, what it is. We are going through the one, I think, I guess it's not even a survey paper. It's more of a, they literally, I think in the first sentence at the start say, this is an opinion paper. Um, I don't know if that's really different from a survey paper. I guess it kind of is. An opinion paper is mostly, I guess the difference would be that in a survey paper, it's less trying to be convincing, I guess, and it's more like this is where things are and this is where they may go, as opposed to, I guess, say an opinion paper is more so, you know, I don't know. I feel like they kind of blend together. I think. Anyway, doesn't matter. Semantics, whatever. So anyway, all of that is to say that it's not really a research paper, but it's a good introduction to the concept of machine programming. And even though I'm very new to the idea, it aligns with lots of things that I've been ruminating over for quite some time now. And this just kind of puts a formal, I guess, conceptualization on those ideas and really, grounds it in actual work that is being done, in a field of computer science. And I mean, really, the short of it is as um, artificial intelligence becomes more and more capable, which they are. I mean, if you think about how things have been happening for the past 2 or 3 years, they just keep getting more capable. I mean, yes, you can make the argument that a lot of that um, progress has been down to basically throwing more GPUs at the problem, but I don't think that that's entirely fair. I'm sure that there's been, well, speaking as somebody looking in from the outside, not actually having any um, deep understanding of um, I guess the actual machinery of things. Um, yeah. Anyway, even with that lack of mastery over the fundamentals of how these things are built, it does appear that there is. It's not that I don't think that people are just throwing more GPUs at the thing. I mean, at the models. There's some cleverness and some, work that is being done to make improvements that uh, uh, I guess keep up with uh, are meant to extract the most amount of value from the amount of investment, the capital that is being thrown at this, you know, this technology. Um, so yeah, so as these things become more and more capable, I think software engineering as we know it is going to drastically change, at least for the people who continue on to be software engineers. Yeah, it's probably gonna change to be more aligned with what's being described in this paper, you know, being machine programming. Anyway, so let's just follow up, I guess continue on. Last time we stopped at section 3.3, so we'll get started with number 4. And just, I think, as a review, I think 3 pillars, and I think I remember this right. The 3 pillars are, so there is intention, right? You want the quote unquote system, this machine in this machine programming paradigm, you want the system slash machine to be able to lift the intention out of the I guess artifacts or assets of the well, I guess not just the system. Anyway, I think the point is that you want to have a sophisticated way to extract meaning from actual source code or other documents that are relevant to build a fully a full picture of what it is that you're trying to build, or the system, the software system in question. So that's the intention part. Then you have the I think it's the invention, right? I'm trying to remember this from memory instead of just looking it up. So there is the invention, and then there is the adaptation, right? The adaptation is the part where you're not just talking about greenfield projects, right? It very much takes into account the fact that a big part of software engineering is the ongoing cycle of just the progression. Code never just stops. At least code that's useful and critical to the functioning of a business never just stops, right? It's evolving. There are new requirements that come in, or bugs, or things that need to be fixed, improvements, refactoring, whether it's for security, performance, or even just quote unquote test, I guess, reasons. Your software is more often than not evolving, changing, and so that's the adaptation part. Okay, so part 4, adaptation. Determining the algorithmic. Oh, I can't speak tonight. Algorithmic steps. Okay, determining the algorithmic steps to solve a problem is only one part of the software development process. The resulting algorithms must be made to run efficiently on one or more target platforms, and after the code is deployed in the field, the code must be maintained as users expose bugs or corner cases where the system does not behave as expected. Moreover, as workloads on a system evolve, it may be necessary to evaluate optimization decisions to keep the software running at its peak performance. Together, these capabilities make up the adaptation pillar. Pre-deployment optimization. In recent years, there have been significant efforts in automating the work to adapt an algorithm to perform optimally on a particular platform. To some extent, the entire field of compiler optimization is dedicated to this goal, but recently there has been a strong push to move beyond the traditional application of predefined optimization steps according to a deterministic schedule and to embrace learning-based techniques and search in order to explore the space of possible implementations to find a truly optimal one. A turning point for the field came with the advent of auto-tuning, first popularized by the Atlas and FFTW projects in the late 90s. The high-level idea of auto-tuning is to explicitly explore a space of possible implementation choices to discover the one that works most efficiently on a particular architecture. I just noticed that I'm really off center on my camera. Something to do probably with the AI tracking stuff. Okay, I think that's better. Somewhat. It's fine. Alright. The Petabricks language. Don't need this. What is this here? Okay. The Petabricks language pushed this idea all the way to the language level. Petabricks. Never heard of it. Never heard of any of this. Well, the concept of index structures. I think I've come across that quite a bit in a database world, because obviously index structures play a big part in database systems. Anyway. Push this idea all the way to the language level, allowing the programmer to explicitly provide implementation choices throughout the code, replacing all compiler heuristic with reinforcement learning to discover close to optimal implementations. Starting in the mid-2000s, there was also a realization that domain-specific languages offered an important opportunity for automation by eliminating a lot of complexity of fully featured programming languages and exploiting domain-specific representations. DSLs enabled aggressive symbolic manipulation of the computation, allowing the system to explore a much wider range of implementation strategies than what a human could possibly consider. Spiral and the tensor contraction engine were early examples of this approach. More recently, Hadidi. I'm gonna go with Hadid. Oh, what happened? Now I'm really off the mark here. Oh shit! I forgot to. Gosh, I forgot to recalibrate my. All right, here we are. Cool. Um, excuse me. It's been a long day. Um, More recently, Khalid, I'm just gonna go with Khalid, has demonstrated the potential of this approach to bridge the ninja gap by generating code that significantly, gosh, I can't read, outperforms expert tuned codes with only a small amount of high level guidance. Interesting. Oh wait, yeah, I mean, I think I've heard of this. It's for image processing something. Yeah, I'm talking about the language. Okay, just means to write high performance image and processing code on modern machines. It's embedded in C++. You can write C++ code that builds an in-memory representation of a high-level pipeline. You can then compile it to an object file. The following function defines as a schedule for it. Okay. Well, like, do they have concrete things to look at? Example apps. Oh, they have a WASM thing. I'm always interested when something can transfer to WASM. Call CPP. I mean, I don't really know what there is going on here, but I just want to get a feel of what it looks like to use it. Oh, so there is a runtime that you can embed here, or at least, well, you can define a buffer that is specific to that runtime. Yes, compatible if you want. I don't do a lot of image stuff, so it's kind of for resize. I think that should be pretty. Oh, well. So, wait, is this the one that's generated? So this is the generator. Or is going by the name? Wish there was something to look at to quickly see why you will use this as well. I guess the reason is it can be way more performant. We have lectures. follow machine schedule carries out the mechanical task of generating. Unfortunately, design hard perform blah blah blah. Our solution extends the function bounds analysis already present in the Howley compiler to automatically perform locality and blah blah blah. The algorithm does not require costly auto-tuning and generates schedules for a broad set of image processing benchmarks.
Hi, I'm Andrew Adams. I'm one of the creators of Halide, and this video is a demonstration of how I use Halide in my day-to-day job to make image processing code go fast. Now, a lot of the tools I'm going to be using and the things that I'm going to do aren't going to make any sense to you if you haven't already done the Halide tutorials. So I recommend if you haven't, go do those first and then come back to this video.
Let's give it a chance.
That was someone posted on GitHub on the Halide project and asked for help scheduling. It's a very straightforward blur. So if we look at this, we include the Halide header, we use the Halide namespace, we define this generator class, and a generator is the unit of Halide code that you use when you're doing ahead of time compiled Halide, which is what most companies do. We have an input that's uint8, two-dimensional, and an output that's the same. And then we have a generate method that actually defines the algorithm. So we declare some variables, we have a boundary condition to the input, we upcast to 16-bit, we blur in X, we blur in Y, and then we downcast the result back to 8-bit. Okay, so this code currently has no schedule at all, so it will by default aggressively inline everything into the output. For a lot of algorithms, that will take the age of the universe to compile, but for this one it's fine. Fully inlining everything is actually a reasonable choice here, so we'll just proceed and compile this and see how it works. Okay, so what do I have in this directory? Nothing else. So let's compile this blur generator file. Okay, so we need to point it to a Halide distribution. I have one freshly built over here. Okay, now I need to link it to libhalide, because libhalide is the compiler. We don't have int main. So these generators need a sort of stub int main to get them going and to actually serve as the entry point to the binary. That is in tools, it's called GenGen. Okay, so now we have a compiled generator. You can't find libhalide.h. You could set LD library path. I like to use rpath to just tell it where to look. Okay, we have a generator. Let's not call it a.out though. I'll make a bin directory. We'll call it blur generator. Okay, so what can I do with this compiled generator? Well, there's one generator object inside it, and I want to select that one. -O must always be specified. I want to specify where the outputs go. Target is missing. I have to specify what target I'm compiling for. I'm going to use x86-64 Linux AVX2. Okay, that seemed to work. Let's have a look in the bin directory. We have a static library with the compiled code. We have a blur.h, and we have this registration file, which will be useful later.
Okay, this is...
Okay, so we have some forward declarations. We have our buffer.
Okay, this is becoming a detour. Oh shoot. How do I find what I was looking for? Wait. Has my screen not been moving this whole time? Like, because I've been reading the stuff and... Oh no. Oh no. Well, that's a doozy. At least from my perspective, it looks like it was stuck on the initial frame, like at the very beginning, and it hasn't, because I've been scrolling down and it hasn't changed. At least the image that I'm seeing indicates that it hasn't changed. I think I can do properties and then restart capture. Okay. Oh well, we move on. As long as the audio was okay, we should be okay to move on. At least, keep going with where we were. More recently, Holiday has demonstrated. Okay, yeah, we ended up here. Um, Despite this success, there's a significant scope for advances in this direction. For example, how do we enable transfer learning so that the nth program can be optimized faster by leveraging learn optimization from the previous n-1 program? Yes, this is something that has crossed my mind. I think part of the software 2.0 stack is gonna be it's going to be skilled software engineers actually going through. It's the same way that today you have people who literally they just sit down, and annotate videos or annotate documents as a data curation process. Because I mean, if it's something that we've known and that is, always proving itself to be right, it's the fact that the higher quality of data you're able to provide, the more likely you are to get a better performing model. Like the quality of the data makes a big difference. And so as we move towards a world where we want the AIs to generate, high quality software, especially, when we think about optimizations that are target specific, you will need people who can annotate what does a optimized program look like for annotating what the program is supposed to be or supposed to be doing. Probably annotate the fact that there is a standard I guess normal version of the algorithm and what an optimized version looks like. Yeah, I think there's going to be a need to really annotate a whole lot of the existing code across different languages. Yeah. And I mean, I guess I haven't really looked at the kind of data sets that are being used right now to train these models that are supposed to be specialized for coding. I don't know exactly the kind of data sets, or at least what that looks like. So maybe, I mean, I wouldn't be surprised if that's something that, I don't know, maybe an Anthropic, the makers of the Claude model, are already doing to some extent. But yeah, code mining, I think I call it code mining / code annotation, is gonna become pretty significant, or I guess a big part of the software 2.0 stack, which I think will be in big part driven by the advent of machine programming. Could learning help reduce the cost of developing high-performance DSL, for example, by reducing the need for custom heuristics optimizations? That remains to be seen, because if there's one thing that we are learning, more often than not, what happens is when you have a model that is laser focused on a particular set of tasks, it tends to perform better than models that try generalist and be good at everything. Well, I guess, yeah, be good at everything. Um, Post deployment maintenance. One of the most important maintenance tasks today is the repair of bugs and vulnerability. Fixing software bugs is currently an entirely manual process. A programmer must diagnose, isolate, and correct the bug. While the bug remains in place, it can impair program behavior or even open up security vulnerabilities. Recent research has demonstrated that demonstrated the feasibility of automating many aspects of repair to the system include Clearview and GenProg. Don't think I've ever heard of this. Either one of these. Clearview uses learned invariants that characterize correct execution to generate patches, which can be applied to a running program that repair a range of execution integrity defects. That feels like some simulation testing, simulation / prop testing thing, except the system doesn't just flag the defects, but it makes attempts at fixing the defects. GenProg uses genetic programming to search for patches for defects exposed by input-output pairs. More recently, Fernand and Martin have pioneered machine learning mechanisms for automatically generating patches for large software systems. Huh. Never heard of these names before. Let's do a quick Google search. Have they done something recently? So this is definitely the latest page. Cryptocurrency. So the scalability of blockchain. 1,000 transactions per second. Minutes. It's still not great, but it sounds like an improvement, because I think I used to hear hours. I mean, I'm sure there are systems that still do hours right now, because I mean, this seems like a new. I will assume that this is a new thing. It's probably not even deployed anywhere yet. Conflux records additional information between blocks. No, that's not a good sign. Oof. Okay. Shrek is a no transaction with a protocol file. I'm not very interested in the blockchain stuff, if I'm being honest. Okay. So this is more in line with what we were, what we are reading about. Yeah, you wrote a lot of code. Okay. How old is this? 2015. Jeez. Okay. So this is more recent because it said 2024. So this is some blockchain stuff. Feels like blockchain stuff again. Yeah, I think he's been focusing more on blockchain stuff recently. Oh, this is some GPU stuff here. Back to blockchain. Oh yeah, where are we with zero knowledge proof, by the way? We should really be getting to that sooner rather than later. I feel like this is gonna be big for social sites. Well, actually, to be specific, more like dating website, for example. With the advent of AI and all that. I mean, there are many more use cases for zero knowledge proof, but it will definitely be useful for social media stuff. I mean, assuming that social media websites are serious about not having a dead internet situation. And also not being overrun by, trolls and whatever. Yeah, just a bunch of. This feels more like it's in line with what we are currently reading. Okay, this one here. Wait. This study explores the utilization of intermediate languages, including various programming languages, natural language solutions, and pseudocode, and systematically evaluates the impact on performance of LLMs to code generation tasks. Our experiments encompass encompass 11 models across the Codellama, GPT, and Mistral family, as well as newly released smaller models. Our findings, let's zoom this in. Our findings reveal that intermediate languages generally exhibit greater efficiency in larger models that have not yet achieved state-of-the-art performance. Natural language consistently emerges as the most effective, intermediate representation across all target languages. Really? That's interesting. If you think about it, these models are overwhelmingly trained on just text data that's not coding, right? Like, just content. So its way of deriving semantics from, prompts and all that in natural language is arguably superior to compared to just coding text. I don't know. It's still a little bit surprising. Um, Considering how lossy natural language can be. However, we observe no universally effective intermediate formal language across different models and target languages. Further, we uncover a weak correlation between the correctness of intermediate solution and final generation. Huh. So it doesn't matter how great your intermediate specification is, it it just doesn't guarantee correctness on the output program from the LLM. I mean, again, it depends on what you're trying to do. If you're just specifying the addition operation, I don't know, I feel like it will get it just fine. Suggesting that improvements may stem from the chain of thought effect rather than language specific transfer. Okay. Interestingly, we discovered that for GPT family models, prompting multiple times without explicit self-correction. Self-correction instructions yield performance gains across the study language. Wait, so this means that when it gets stuff wrong, instead of telling it that you got it wrong and trying to give an instruction to self-correct, you just prompt the same thing again. That's so counterintuitive, though. It's like just repeat yourself, and the model will internalize the fact that, oh, this is insane. Why is this person reprompting the same thing? It must mean that I'm doing something very wrong and I need to change my ways. Because that is a very strange behavior. Like sounds like it's a much stronger signal if you think in terms of reinforcement learning. It's a much stronger signal, I mean, according to this, to just reprompt the model with the same prompt rather than try to self-correct it. That's well, at the very least, that's unexpected from my end. Okay. This research has highlighted the importance of learning and statistical techniques for program repair. At a fundamental level, program repair is an undetermined problem, so a repair system must be able to select among all the possible patches that eliminates the symptoms of the bug to select the one that actually eliminates the bug without introducing other undesired behavior. This can be done by automatically learning invariants that characterize correct behavior so that the generated patch can be required to maintain these invariants. Yeah. By using required to maintain these invariants by using machine learning over a large corpus of real bug fixes to build a model of successful patches using change statistics from past human patches, or even leveraging a large corpus of bug fixes to learn how to generate successful patches. Other successful program repair techniques focus on specific classes of defects, such as incorrect conditionals, here constraint solving can play an important role. Automating repetitive source code edits can also eliminate the core errors or correct errors, introduced by developer mistakes when working with similar code patterns. Code transfer, potentially augmented with machine learning to find appropriate code to transfer, can automatically work with code across multiple applications to eliminate defects and security vulnerabilities. These demonstrated techniques lay out the initial case for the feasibility of automated bug detection and correction autonomously without programmer involvement. Many existing successful techniques focus largely on surviving execution integrity bugs that can cause crashes or open up security vulnerabilities. Future directions include the additional incorporation of machine learning to enhance current latent bug detection techniques and generate more sophisticated corrections for larger classes of bugs. In addition to bug fixing, there are a number of other post-deployment maintenance tasks that can benefit or that could benefit from learning. In general, these fall into the category of bit rot prevention and include, for example, upgrading to new versions of the web services. Oh yeah, that is not fun when you start doing that. Porting to new platforms such as new cloud or mobile environments or specializing code for particular users. We envision the eventual development of systems that continuously monitor program execution, incorporate feedback, and learn from large code repositories to deliver a system of autonomous and continuous program correction improvement. That's weird. Yeah, I mean, this goes back to here, this part, learn from large code repositories. That's basically what I was talking about in terms of code annotation or code mining. You're gonna need people to actually sit down, and basically it's you crowdsourcing the process. I mean, you have to make it worthwhile, but you also don't want a case of quantity over quality, right? So there's a balance there that you need to find where you're not just selecting anybody, to do this annotation process. And I think you need to have it in such a way that there's a process by which, so let's say somebody's is assigned a code base to look at, right? They say they're really good at Rust or they're really good at Go. There is a what's the word? Anyway, there is a backlog of Go curated repositories, or even if you want to be more specific, Go packages across, I don't know, the internet, mainly GitHub, uh, and you get assigned one, right? And so maybe for the next 3 days, your goal is to extract, you know, algorithms and data structures and patterns and annotate that all over the code base. And it should be a process by which it's not just one person. Like, just because somebody found, I don't know, some compression algorithm and labeled it as such and give it a rating or whatever, doesn't mean that that's final. Like, obviously, and I'm sure this is already the case with just the way we annotate documents and um, um, text and videos, images, whatever. You definitely need a process where multiple people get to uh, review each other's annotations, including possibly proposed annotations by AIs, right? And so at the end, you basically get um, maybe for the same algorithm that was mined for that, from that code base, you have 5 or I don't know 7 different annotation uh, records, and either you keep all of them, right, or you have a process by which you only keep, I don't know, 3 of them, but that process needs to be solid. Maybe that's also some sort of LLM as charge system where it looks at historically. I mean, based on the people who made the annotation. I mean, obviously, and this is tricky, right? You could look at the record of those people who are doing a review, and obviously, if you have somebody who's, I don't know, a 10-year PhD computer science, well-known researcher from, I don't know, Stanford, who annotated something that holds more weight than some freshman college student from, I don't know, what's a really good, I mean, there are many good computer science universities, University of Maryland or Waterloo or, I don't know, Berkeley, right? I mean, still very good, well, probably very good student, but you probably are putting more weight on what the researcher from Stanford has labeled the thing. So you need a way to account for that, and maybe yes, you probably keep all the annotation records, but then you have some sort of weighted process by which there's a weight associated with each of those records, and that's taken into account when it comes down time for the automation processes to decide whether to pick that particular piece of code or not, right, for a particular context. Anyway. Okay. Part 5. The interplay between pillars. Systems for machine programming will most likely be composed of a set of tools, each of which focuses on a particular pillar. We anticipate that in most cases, an individual tool cannot be fully understood in terms of a single pillar. The machine programming problem is multifaceted, and issues concerning one pillar will it's getting late, isn't it? Having some trouble here. Will inevitably impact the other pillars. Hence, we need to understand machine programming systems in terms of the interplay between the three pillars. We expect this interplay to expose a tension between features of a tool that is supportive of the needs of any given pillar and those that are disruptive to the needs of the other pillars. The challenge is designing a machine programming system. No, the challenge in designing a machine programming system is to understand this interplay and reach an effective resolution of those tensions. As an example, to explore this interplay, consider verified lifting. Verified lifting tools input code written in one language, translate the code into a new language, and then formally verify that the new code produces results that are consistent with the original code. The prototypical example takes stencil codes written in an imperative language, translates them into a modern DSL such as Halid, and then uses theorem proving technology to verify that the original and generated DSL codes are functionally the same. The newer code defines an abstract representation of the problem that can adapt onto a wide range of computer systems. Therefore, we see that the verified lifting problem is primarily used to support the adaptation pillar. Oh, it's weird. A very random thought just crossed my mind, and I actually don't know if I want to share it, because it could be worth billions of dollars. Well, okay, maybe not billions, but a lot of money. Well, shit. Yeah. That I have a feeling that with the right distribution, the right marketing, yeah, I think it's within a year or two, it's probably gonna be cursor level of hype. I mean, hype as in, you know, uh, you know, growth and all that, and adoption. Sorry. Anyway, verify. We'll see. Well, if I actually sit down and start prototyping stuff, which actually shouldn't be that damn too much trouble, I guess. For what I'm thinking, I mean, besides training a model as a co-pilot, you will need buy-in for a certain target audience for them to be shepherded. Well, I don't know, is that a right word? Yeah, anyway, yeah. It's, I don't even know why. This is just me talking out loud. Without the actual context of the idea, I imagine that none of this actually makes sense listening to me. Anyway, well, the part about the idea, I hope everything else that we've been reading has made some sense to you. Consider the early steps in the verified lifting problem. Wait, didn't we just read through this? Oh no, okay. Okay. Let's keep going. I don't think we read this. A verified lifting tool must first understand the problem as represented in the input code. Yep, challenging. It discovers the intent of the program, challenging, and produces an internal high-level representation of the problem, often in mathematical or functional terms. Excuse me. The phase of the verified lifting process is firmly grounded in the intention pillar. Yep. From the high-level representation of the original problem, The Verify Lifting system can explore a range of algorithms appropriate to the target language. Therefore, working within the invention pillar, it then synthesizes the new code. The adaption is it just me or it should be adaptation, right? Yeah, adaptation. Oh, yeah, there's a tation missing, right? I'm not crazy. Okay. Oof. It's about to be like, I know it's late, but it's not that late. Like in life in general. It's not that late that that this word is actually what, like real. At least in this context. Um, it says the new code, it then synthesizes the new code and verifies that it is consistent with the high level representation of the problem. Hence, the Verify Lifting tool, while normally focused on adapt. Why do they keep using this word? Like, is this okay? It's only showing up twice, so I think there's a strong chance that this is a mistake and they're not trying to mean something else or whatever. I introduced a new term or something. Okay. Well, hence a verified lifting tool, while nominally focused on adaptation. No. Gosh, now I'm confused. Adaptation. Sorry. Yeah. Touches in a supportive way all three pillars. It is important, however, to consider ways that a tool disrupts analysis within the different pillars. For example, when Verify Lifting translates low-level code into a compact representation in DSL, it's making the intent behind the code more apparent. Yet, the transformation can also interfere with other tools at the intention layer. Okay, for example, if the lifting transformation is not careful to preserve variable names, it may hamper the performance of intention layer tools that focus on names in a code to estimate whether a piece of code is relevant for a particular task. In general, when adaptation finally layer tools modify code, it is important to think about how the change may impact. Wow, for some reason I thought this came out in 2021, but this is 7 years now. I'm very surprised that I just did not, like it didn't we didn't cross path whatsoever in this. Gosh, 2018 was 7 years ago. Just kind of insane to think about. Anyway, so much has happened since then. Oh yeah, that was COVID. Well, no. That was way before COVID. That was 2 years into the first Trump term. It is important to think about how the change may impact the ability of intention and invention layer tools to use that code. While we have discussed the interplay between pillars in terms of just one machine-based programming technique, We expect this complex interplay to be a common feature of machine program systems as researchers in machine program apply the three pillars in their own research. It is essential to consider the interplay between the three pillars and how this interplay is supportive or disruptive to the overall programming process. All right. Data. Nearly all machine programming systems require data to drive the algorithm. Yep. I'm gonna really get in that code repository. Like, I feel like let's say with the advent of AI, you could make the case that the bottom 40% of the software engineering field gets blitz. That's an argument you can make, although some people will argue that with AI being what it is, as a if we reach AGI or whatever, then everybody's a software engineer. That can also, I can see somebody making that argument. Anyway, the point is that I think what I want to get at is that there will be a significant portion of people in software engineering / machine programming whose job will be to, and again, I think this aligns with Andrej Karpathy's vision for software 2.0. There will be a significant portion of the workforce that is labeling data. But then I guess if the AI is actually AGI, you could also argue that why isn't it doing the annotation itself? It will need to have people with very specialized skills of, certain special areas of computer science to screen code. Like, the Linux kernel is pretty big code. I think you'll need, I don't know. I think you'll need people who have been kernel. You'll definitely need people who have been kernel contributors to partake in this exercise of annotation. Right? If for example you're trying to have a system that can automate custom built kernels for some systems, you'll probably need people who actually worked on the thing and have some idea of how things are supposed to work. Although I hear a lot of people talk about it's not uncommon to read the man page and realize that there are multiple realities of what multiple realities involved. There's the reality of the manual and the reality of the code and the reality of the people reading the code. And or claiming to understand what the code means or is supposed to do. Anyway, yeah, let's keep going. More specifically, every research area listed in tables 1, 2, 3. Well, the tables, I'm guessing they're down here somewhere. It's fine. I'll go through that. Requires data in some form to function properly. The data required by these subdomains comes in a variety of forms: code, input, output, examples, DSLs, etc., but is ever present. This dependency on data makes it essential that we consider the open problems and emerging uses around data when reasoning about machine programming and the systems that implement it. The various approaches to address the three machine programming pillars have different needs in terms of the type and size of data they require. Moreover, there is a wide spectrum in terms of the quality of the data that a project may use. Yeah, quality of the created data from all the sources, right? Code, input, example, and all that. We discussed some of these emerging data use cases and issues in the remainder of this section. Code repositories. Large version control repositories such as GitHub offer the promise of access to full revision histories for all the code necessary to build and run a project, as well as its accompanying documentation. Yeah, so it's not even just the current state of the branch, right? It's the full commit history that can actually help in understanding why, like the actual feature, like how features have been added and evolved over time, the bugs that got introduced and how they got fixed, and how those fixes may have introduced latent bugs in other features that nobody has noticed yet. Yeah, it's a lot of data, and especially now that AI is generating so much code. Yeah, I mean I feel like that would be GitHub's moat because they have access to all that data directly. Like it's not a third party thing. Like it's first party data. First party data is always golden, assuming that the data is useful and not completely trashed. Many projects in these repositories have long commit histories with detailed commit logs, which could be of notable value to machine programming systems. However, recent analysis of public repositories have shown that a large fraction of the projects are duplicates. You're gonna have to be smart about which repositories you pick. I mean, obviously, it's easy to pick something like ClickHouse, right? Like a project like ClickHouse. I'm sure there's a treasure trove. Well, it is a treasure. Gosh, it's getting late, so the words are slow to come out. I'm sure that the ClickHouse repository is a treasure trove of data about algorithms, data structures, patterns. Yeah. I mean, there are many other projects that you can. I mean, Postgres, MySQL. MySQL. Although Yeah, I don't know if the code of MySQL is public. I mean, I know Facebook has a fork of MySQL. All the, I mean, the DuckDB code is probably really interesting as well. All the Arrow stuff. Obviously, Rust is relatively new. I mean, it's been around for a while now. Yeah, there's so many code bases that are, I think most people will agree, are high impact, high. Um, oh, okay, high impact, at least decent quality um, code bases that you can extract very very high quality information from for this machine programming system things. Uh, this type of data utilization has been explored to train models for program repair. Additionally, the presence of complete code bases make it possible to run whole program analysis on the code. In some contexts, it has been shown that augmenting the code with features discovered from program analysis can help train effective models. However, complete code bases may not always be available, and running whole program analysis may not be feasible. Incomplete and synthetic code plus natural language. Sources such as Stack Overflow provide a wealth of information beyond code, which can be used to correct code in natural language. There has been some work in the community in extracting information from code that comes in the form of code snippets, like those usually found in Stack Overflow. This requires assembling information gathered from multiple different snippets in a coherent model of the behavior of a code component, or into a coherent model of the behavior of a code component. Okay. There have even been some effort aimed at extracting code from video tutorials. Interesting. Which offers the possibility of correlating the code with the accompanying narration. In some contexts, the data needed to train a model does not even have to come from real code. Synthetic data generated from random combinations of components can be useful as demonstrated by DeepCoder. When did this DeepCoder thing came out? 2017. That was a long time before even. Oh, wait. Is this the commercial version? I guess whoever was working on this monetized it? Or is this something else that's using the same name? Oh, okay, somebody did an implementation. I wonder if this is the same person who made the website. I mean, I gotta try, right? There are exactly three. Get easier in one way or another. It's in the code from. Saudi uprising. This is all the way back in 2017. First they came for the factory workers, then they came for the accountants, then they came for the drivers, then they came for me. Well, I wonder how that person feels about things these days. I mean, I could probably look up the post history for that, but yeah, it's fine. Program is easy if specs are frozen. I want to see the neural network discuss with my managers about inputs and outputs. I mean, today we are closer than ever to be able to actually have this be a real thing that is actually useful. Yeah. Anyway, let's get back. Data privacy. One of the open issues of machine programming data is that of privacy in the context of code. Machine programming systems will eventually have to work with and protect intellectual property as well as software licensing agreements. Yeah, that's actually an interesting aspect because you could argue that somebody's sitting down and curating a high quality data set of, annotated algorithms and data structures from various sources, GitHub repositories, research papers, I don't know, all kinds of sources anyway, books, videos, whatever. You could argue that that data set doesn't have to be for free. I mean, probably won't be because once you realize how valuable such a data set can be when it's really good, right? When it's well curated and all that, then, that's really valuable. And if you're a developer and you're good at doing that, you probably want to monetize that. So now you need to think about how to set up the incentives, right, for the system to work well. As we move toward a future where data will be more openly shared, used, and traded, yes and no. Because I think people are gonna start waking up to the fact that they probably cannot compete on the compute ground with these hyperscalers. I mean, how many people can just decide to, build the biggest cluster of GPUs somewhere in Texas? Like, there are very few people or organizations that can pull that off. So computing on compute is not really an option for the vast majority of enterprises. So now you really are talking about having some economic success in the market. To have some success, you start realizing that the data, your first party data, can be very valuable. And so, yeah, I don't know. This idea that it's all gonna be openly shared and used and traded, we'll see. New models and tools for secure and privacy preserving exchange will become increasingly important. Yes, I agree. I mean, yeah, if we figure this part out, then yeah, because you know that there is a way for you to track the efforts of your curation and to potentially uh, get compensated for that work at market value. Yeah. In the case of models learned from code, there are important open cyclic questions surrounding the copyright status of the code generated from models trained from code. Yeah. Yeah, that's. I mean, we already have that problem right now. It's just that I don't know, for some reason we just decided that it doesn't matter. When you think about how these models have proliferated, and I mean that's probably a good thing. I think. Um, yeah, I think you can make an argument on both sides. Solid argument on both sides. Lifecycle management. Machine program systems require lifetime management practices similar in scope to those in traditional software engineering. Much of this is due to the need to fulfill the goals of the adaptation pillar. Yep. And I think this is the part where the part that motivates, I think, the idea that there'll continue to be people working in the field. Like it won't completely die, basically. This lifecycle management efforts will be long-lasting and require support for continued monitoring and improvement around changing software needs and advances in an increasingly complex and heterogeneous hardware ecosystem. A significant portion of this life cycle management will be centered on managing the data that are required for such an adaptive machine programming system. As these data will help ensure the stability and maturity of the system. As machine programming systems evolves, so will the data then just to baseline, so will the data then just to baseline and advance the system. Because of this, proper data management is likely to be a key enabler to calibrate any machine programming system's life cycle. In the post-Dennard scaling world, where performance comes from architectural innovation rather than increased transistor count, the constant power density hardware complexity will only increase. Heterogeneous computing will become more widely used and more diverse than it is today. Over the next several years, specialized accelerators will play an increasingly important role in the hardware platforms we depend on. At the same time, the nature of programming is changing. Yes, indeed. Instead of computer scientists trained in the low-level details of how to map algorithms onto hardware, programmers are more likely to come from a broad range of academic and business backgrounds. Moreover, rather than programming in low-level languages that interface almost directly to hardware, programmers are more likely to use higher-level abstractions and scripting languages. Just use SQL. SQL is the answer to everything. I'm 60-70% joking. There is a way to bend SQL in such a way that you can use it as a DSL to send those programs. And it will actually be useful. I'm like pretty confident on that front. SQL, all the things. This will fundamentally change how we write software. We believe this change is already well on the way. We envision a future where computers will participate directly in the creation of software, which we call machine programming. This paper presents a framework to organize work on this problem. We call this framework the three pillars. The three pillars are intention, invention, and adaptation. Intention focuses on the interface between a human and machine programming system. Techniques to discover what a program needs to do from input that is natural to express by the human. A system grounded in the intention pillar meets human programmers on their terms rather than forcing them to express code in computer hardware notations. Let's read that again. A system grounded in the intention pillar, okay, meets human programmers on their terms rather than forcing them to express code in computer hardware notation. But I mean, if there are human programmers, you will kind of expect them to some degree express what they need to express, even if it's in a DSL. Yeah, I mean, I get what they're trying to say. Invention emphasizes machine systems that create and refine algorithms, all the core hardware and software building blocks from which systems are built. Adaptation focuses on ML-based tools that help software adapt to changing conditions, whether there are bugs or vulnerabilities found in an application or new hardware systems. Data is at the foundation of the modern renaissance in artificial intelligence. Without vast amounts of data, it is unlikely that AI will have had significant impact outside specialized academic circles. In this paper, we explored the impact of data as it pertains to machine programming, software repositories in systems such as GitHub, and a vast amount of software embedded in countless web pages is the raw material that will likely support a large majority of the emergence of machine programming. Finally, there are numerous open problems that must be solved. We outline some of these open problems. It will take a large community of researchers, years of hard work to solve this problem. If we can agree on a conceptual framework to organize this research, it will help us advance the field and more quickly bring us to the world where everyone programs computers on human terms, with machine systems handling the low-level details of finding the right algorithm for the right hardware to solve the right problem. All right. Well, that was awesome. Well, I guess just the whole idea of machine programming is pretty awesome, I must say. And I am optimistic about these systems coming alive and just, really transforming software engineering. And I think it will be for the best overall, because, things are far from being perfect right now. But, we've made it work, and I think we definitely should, we are definitely open to the idea of moving the field forward into this new into a new age of machine programming systems. I am very excited about that prospect. I'll probably at some point on my own time, maybe not, probably not on stream, go through some of these citations. Well, by go through, I mean just really skim, really abstract, and only curate a few to actually sit down and fully read through. I would suggest that you do the same. Yeah, I think we are done for tonight. I hope this was useful, interesting, and it will motivate you to do some further exploration into the topic and, start thinking about how you can contribute to this new paradigm for software engineering. All right. Good night. Thank you for your audience, and I hope to see you around.